So welcome everybody. I hope you're all excited to learn about machine learning today. Is anybody a machine learning engineer or a data scientist already, or are you just kind of starting out for the most part? Excellent. So I am really happy that I added in some introduction slides. So today we're talking about overfitting and machine learning in general. And that is the topic of the talk. So who am I? I am Paige Bailey. I do things with computers, more or less efficiently, more or less well, hopefully. I work for Microsoft. Up until just recently, I was a data scientist in the energy industry for about 4.5 years. I have 10 years experience with Python, 4 with R. And I really love kind of the Apache open source products for Hadoop. So if you want to talk about Spark or Hive or something like Impala later, I would love to talk about architecting those systems. And what I do at Microsoft is I am something called a cloud developer advocate, which nobody knows what that is. So basically what a cloud developer advocate does is there's a compute platform called Azure. Azure does a lot of things. And what I specialize in is machine learning and artificial intelligence. So how to use historic data and data that you're pulling in to make predictions about the future. I think it is the coolest thing that you can do with computers because it's the closest thing that you can do to magic, right? Like you have historic data and you're using it to give you some insight into the future. So why is machine learning important? Well, it's because of that, right? So if you have data on your historic customers, if you have information about sort of scientific processes previously, so climate data would be an example, you're able to use that historic information to make insights and hopefully make money, right? Like you want to be able to make decisions accurately the first time. And make predictions accurately the first time and not have a whole bunch of guesswork involved. So since a lot of people didn't seem to raise their hand when I asked about machine learning before, we're going to talk about what it is and what it looks like in terms of code. Because there's a lot of sort of stigma about machine learning right now that it's hard, or that, oh, that must be very complicated, or maybe it's very difficult to do appropriately, and that's not the case at all. And you'll actually see that you can build out a predictive model in about 5 lines of code that has fairly high accuracy and also does quite a bunch of things. And that's because the open source communities in R and Python have spent literally decades building out these collections of algorithms for people to use. So is anybody here a Python dev? Excellent, you're my favorite. If you couldn't tell by the stickers on my laptop, I love Python. It is my favorite language, and second only to R. So, first and then R is second, I guess. But Python is wonderful, and there is a collection of packages called scikit-learn that use machine learning algorithms and a visualization package called Seaborn that have some very nice visualizations. So what we're going to do today is we're going to take a look at an example for credit risk. And so we have here my pal Sven. And the good old stock photo Sven. And we know some things about him. So we know how old he is. We know that he's a guy. We know his credit score, and it's bad. We know that he's not a homeowner. We know that he's overdrawn on his bank account, which is, Sven's making some poor life decisions. Maybe he, decided to buy the latest Apple product and whatever. We know that he's at least employed. So that's wonderful. We know that he has an undergrad degree, and we know that he's in debt at least a little bit, a couple of $1,000s. So Sven is wanting to get a loan to purchase a home. And what we're going to do is we're going to try to make a prediction as to whether or not we should give Sven a home loan. So we also have Maria and Jeff, and we have similar information about each of them. And we have all of this listed in kind of a tabular format, right? And this is the structure that you would want to have data in if you pull it into a machine learning model. It needs to be kind of this rectangular format, right? So not any NA values. You want to have like all consistent record lengths and feature descriptions. So whenever I say a record, just think of it as a row in an Excel spreadsheet. And whenever I say a feature, just think of it as a column. So gender, credit score, homeowner status, yes or no, checking account balance, all of those would be considered features in this model. And so what does this look like when we want to code it up, right? So if we want to build a predictive model using these features to determine whether or not these three folks should get a home loan, what does that look like? And as you can see, so Jeff is a little bit younger than Sven, Maria is a little bit older, but they both seem to have a little bit more financial stability. So maybe that would help them out. So we're going to go into a live demo to take a look at what this machine learning model would look like in R. So let me Alt-Tab, and it should be that guy. Good, and you can see it. That's perfect. So this is an example of a machine learning algorithm implemented in R. It's a C 5.0 decision tree. And a decision tree is basically like a collection of yes or no questions based on given feature choices, right? So the first step would be to collect the data. We have 17 variables. The things that we were just mentioning before, those features like their credit history status, the purpose of the loan, the amount that the loan is for, their age, all those good things. So we have 1,000 observations of 17 variables. And we can see that we also have information from these historic people, whether or not they defaulted on their loan. And a default on a loan is like, we gave them $2,000 and then they were a slacker, they didn't pay us back. So that is yes or no, and it looks like we have about 30% no and 70% yes. So most people paid us back, and then there were some that didn't. We also have a little bit of information about those different features, right? So DM stands for Deutsche Marks. So we got this from a German credit data set from UC Irvine. It looks like a lot of people are overdrawn on their accounts in Germany. Don't know what the deal with that is. And then a lot of people wanting loans for kind of this 2 to 3 year range, some for the 6 year. So these values are in months. But yes, so we have about 70 people, or 70% of people paid back their loan, 30% didn't, and we're trying to build out a formula that would tell us characteristics of people who don't pay back their loan. So for the data preparation, we divide up the data into kind of a split. So we have a training data set that we're going to be building our algorithm on, and then a test data set to check to see how accurate our algorithm actually is. And first we want to randomize it, so to make sure that the data is completely, the data has been kind of mixed up appropriately. Like, we don't want to just sample the first 700 values because they're all people who paid back their loan. It wouldn't tell us anything about the people who didn't. So we want to mix it up. And then once we mix up those values, we want to check that we have the same proportions. And right here you can see that we have the same proportions. So our training data set has 900 folks. Our test data set has the last 100. And that's a very nice ringtone. So we've got it divided up 70%, 30%, looks right? So now that we've divided up the data, we're going to train a model on it. And if you want to go back to your boss tomorrow and say that you are now, you should be paid, at least twice as much because you've got data science knowledge, this is how you implement a machine learning model. That is one line of code. and that is it. And so what we're doing here is we've got that sort of Excel spreadsheet looking thing, right, with 17 columns and 1,000 rows because we have 1,000 people. We're removing that last column, so the one that says yes or no, because we don't want to give our model the answer up front. We want our model to be able to test out what it thinks the answer should be. And then we're getting some information about it. So as we can see here, our decision tree model went through every feature and decided based on breakpoints that it assumed to be good breakpoints. It started building out those yes or no evaluations. So what does this look like really? This would say like, okay, well, if we have a person that we give a $2,000 loan and they have minus $200 in their bank account and they've defaulted on a loan before and they're not a homeowner, they're probably not going to pay us back. Whereas if we have a person that we give a $2,000 loan, they have $3,000 in their bank account, they are employed, they have a home, they're probably going to pay us back. So it's just those yes or no decisions. And as you can see here, it's kind of printed off in a nice format. It's doing just that. It's looking to see what the checking account balance is. It's checking to see their credit history score, so perfect versus very good, the number of dependents, so whether or not they have kids. And it looks like you're more likely to pay back loans if you have children. So I don't know if that's like you're afraid your kid's going to get kidnapped. I don't know. But it tells you, it gives you kind of a set formula for what a person looks like who would pay back a loan and what a person looks like who would not. So that's great. And again, one line of code. The other nice thing about decision trees is that you have very clear-cut, very well-defined formulas. So if somebody came to your bank and said something to the effect of, I feel that you did not give me a loan for a discriminatory reason. Like, I feel like you did not give me a loan because I'm a woman or, of my race or something of that nature. You can point back at your algorithm and say like, oh no, like we didn't give you a loan because the computer said this is why we shouldn't. So you can't sue us. Deep learning is a little bit different. How many of you have heard of deep learning? Cool. So deep learning is a subset of machine learning, but it does not give you such well-defined formulas. And we'll look at that a little bit later. So the decision tree we implemented had a 13.9% error rate, which means that it was right a majority of the time. Like whenever we trained it up on the training data set and then tested it on the test data, it was doing pretty well. And we can evaluate it with one of these cross table things. So when did we predict no and it was actually no? When did we predict yes and it was actually yes? And it looks like we were pretty good there. And then going through and improving model performance. If anybody wants to take a look at this, it's on my GitHub and then also hosted on one of my websites. This link will be posted to Twitter later, like immediately after the talk. So what does this tell us in terms of our buddy spin, right? So, from current slide, what does that mean? It means that based on those rules that we came up with, he doesn't get a loan because he's a slacker, but Maria and Jeff do because their credit history is much better, their employment status is much better, and their bank accounts seem more secure. So that is what machine learning would do. It would take historic data, things that we know have happened, we know those characteristics occurred, and then predict behavior patterns for future loan applicants or future other people that are using that. So now we need to talk about what is overfitting. And so overfitting, the best way to really think about it is, do you remember those kids in school that were really great at memorizing things? So like that slide before, that's organic chemistry. So Orgo is all about memorization. You just look at a picture, you look at a molecule, and then you sort of hammer it out each time. This is what it should be. So those kids were great at memorization. They were great at kind of learning those concepts. But whenever they saw a problem that they hadn't seen before, their entire conceptual framework fell apart. They didn't know what to do. So that's kind of what it would be like to overfit a machine learning algorithm. You train it so well, but all the training is done is made it memorize a set formula. So whenever it sees a new piece of data, it has no idea how to classify it appropriately. So that is what, you have some methodologies that assist with that. In terms of the example that we have here, if we wanted to improve model performance, we could look at a whole bunch of decision trees. And this is what that's doing. We're taking 10 trials, and we're kind of taking the best performers out of those 10 trials. So that's a way to collect a bunch of decision trees into one and boost our model performance. So you can see here, before we had 13.9% error. And if we scroll all the way down to the bottom, we should get some statistics about this guy. Yeah. So it's gotten down to 3.4% error, which is much better, right? So we're accurate much more of the time. And if anybody has any questions as I walk through this, let me know. I'm more than happy to take them on the way in. So yes, so that's a way to boost model performance. You also have some options. So say you're a bank and you want to absolutely minimize the number of times you give people money and they don't pay you back. You don't really care if you don't give somebody money and they would pay you back. Like that won't make you go bankrupt. But you really care if you give somebody money and they don't pay you back. So you can weight your decision tree to preferentially not give those no cases. So to optimize to have better performance on the predicted default. So that is machine learning. And overfitting is making it so that your machine learning algorithm does not perform as well as it should on the training data set. So like that first example that we had, it was right, up until about 13.9% of the time, but it was overfit on that 13.9%. So the top 10 machine learning gotchas, right? So we've talked about machine learning, what it currently is, right? And we've talked about overfitting and what that is. It's basically memorization and not knowing what to do when you see a new piece of data. So what are the top 10 ways that you can overfit a machine learning algorithm? And to make it interesting, we're going to talk about Real Madrid. So the owners of Real Madrid have heard about your legendary data science skills, right? And they want you to predict performance for the club in 2018, right? That is your task. That's what they're paying you to do. But it's not just whether they'll win or not, because obviously, but things like by how much, right? So by how many points, or how will individual players perform, right? Or how many successful passes there will be in a specific game, or how will players grow or deteriorate? Like, were they really good last year and then this year they suck? Or will there be a home field advantage, or will they perform better? Will they perform better in away games, right? And so luckily, there is a ton of interest in doing this for machine learning. So there's this thing called football.db, which is a collection of all of the European football games that's available for free on GitHub. So if you want to take a look at it, that's there. there are also a ton of data services that you can pay for that give you information about sports statistics. So this is huge in the United States for baseball. I don't know why, because baseball is boring. And also for things like football, like the football that's the padded and that one, and also basketball. And they get crazy about it. They have sensors placed everywhere on the field. They're tracking like the speed and the acceleration of the balls and where the players are located and all these sorts of things. And the data is really comprehensive. So you can get a lot of great information that you can feed into machine learning or deep learning models. So this is something that I definitely recommend looking into. It's listed in the sources slide at the end. So if you wanna take a look at it, I definitely encourage you. But so example 1, ways that you could overfit. That would be too few samples. So what does that mean in real life? It means only having data for a few games. So if you only had data for like 7 games in 2011, would that really give you great information about games in 2018? No, not at all, right? Or if you only had data for a few players, right? So if you had Ronaldo and those guys on the screen, right, that wouldn't really tell you anything about goalkeepers. It wouldn't really tell you anything about defenders, right? And if you're gauging all of your players like Ronaldo as a forward, then you're going to be really disappointed, right? Because if you're expecting that kind of performance out of everybody, then that's going to be a problem. So the top way that people can overfit machine learning models is by having these very small amounts of data and trying to make big predictions using just that small amount. So an example, another one, would be using old data, right? So if you had information I know this is very hard to see, but it's like goals scored, assists with goals, shots, and fouls drawn, right? Then if you tried to make predictions based on 2010 instead of 2016, you can see there's a ton of variation over that time span, right? So you can't really judge a player's performance for next year based on the way that they were at the start of their career. And extra points for anyone who guesses who this is, right? So this is goals scored. That's assists with goal. Does anybody want to make a guess? Everybody's so shy. It's Ronaldo. But yeah, so that would be another instance, right? Is you're basing information in the future on historic data that would not really be helpful. Example number 3. So your choice of measure, right? So what does a good season look like? Is that the number of goals that are scored by an individual player? Or is it how many games the team actually won? Because that's not really the same thing, right? Like if you make a lot of successful passes and other people on your team get to score more goals, then it doesn't really matter about that player's performance. Or is it the number of shots? Or is it, the number of passes completed? Like what does a good season look like? And that's probably going to change based on the person who's asking the questions. So obviously the owners of the club, they care how many games that are won. And they care about those questions that we were asking before because maybe they want to place bets, I don't know. But a player would have very, very different ideas, right? Like they would want to see better personal performance than the last year. So another machine learning gotcha would be not having a problem well defined, or taking a problem that's well defined for one customer and attempting to apply it to a customer with completely different motivations. So that's number 3. Number 4 would be cherry picking data. There's a lot of problems with this in climate science that people have been trying to point out. But for example, so 2017 is a great year, right? If you're trying to base every year on 2017, then you're probably going to be disappointed in 2018, right? Like you need to have kind of a comprehensive survey of each year before. Example 5, reprobleming. So what does that mean? It means altering the problem so that your performance improves. What you'll see a lot with machine learning is you build out this predictive model. So the one that we were talking before, right? We had a very specifically defined question. So is this person likely to default on a loan? And what we got back was that Sven was probably going to not pay us back. And so if Sven felt really upset about this and decided to say like, oh, well, no, like maybe we should take a look and see what the likelihood is that I will have more money in my bank account next year or something of that nature, or attempting to fudge the question a little bit so that it better benefits him. That would be an example here. So it's the way to put it in plain speech is that you don't like the result that you got, so you try to tweak the result or to tweak your question to make it better fit your results. So example number 6 is parameter tweaking, and parameter is just another word for feature. So this would be only selecting the parameters that you know will give you good results, right? So it would be like removing some of these things about fouls, right? Or removing problems that the player has been experiencing in the hopes that it will make him look better in the next year. So this happens all the time in business, right? Is if you have a particular business unit or portion of your company that's not doing well in terms of making money, you just remove them from the picture. So if you remove that particular portion of your company from your model, then in general you have better performance. So this is just bad statistics, and it's also not very ethical in terms of machine learning practices. So example number 7 would be human loop overfitting. And what does that mean? So there are 2 families of machine learning, right? So there's supervised learning and there's unsupervised learning. What we did before was called supervised. So with the decision tree, we had the answers. The computer was basically, giving us the answer, and we didn't really have to do much. So if you ever hear somebody say, like if your boss ever says, hey, I want you to do machine learning, and you're like, okay, all right, what kind? Make sure that they say supervised, because unsupervised is much harder. So unsupervised is basically you have no clue what you're looking for. You're just trying out a whole bunch of different things and hoping that something pops out. So this is an example of a clustering algorithm, and it's really straightforward to see, right? It's like there's a collection over here, and we'll color it green, and a collection here, and we'll color it blue, and a collection here, we'll color it red. But for the most part, there's nowhere near that well-defined of clusters. So human loop overfitting would be having a human come in and take a look at a bunch of clusters that are really, really close together and not very well defined, and trying to use that to make classifiers that you would put into a supervised model. So it's anytime you put a human into a machine learning problem, you're going to have a bad time. So it's just don't do it. Like, make the computer do the hard work, and then you'll be fine. So example 8 would be collinearity. And that's a bunch of features giving you the same information. So if you had, in the example that we used before, right, we had the age of Sven. And if we also had his birth date, that would be giving us the same exact information in those 2 features. And what it would do would be to kind of skew your machine learning model so that it has multiple information for the same thing. And unfortunately, that would give you really problematic results, right? You would probably get really, really high accuracies for your decision tree, or it would kind of confuse the decision tree. Either way, it just wouldn't be a good time. Same for the example with Real Madrid players, right? So age, date of birth, and years playing professionally, they would probably all kind of be correlated. So overfitting by review. This is a huge problem in academia. So in academia, you have 10 papers that are submitted to a journal, right? 10 papers, 10 different topics, and the journal can only select one. The one that it probably selects is the one with the highest accuracy. It doesn't matter if that's the one with the best research, right? It's the one that the journal decides to select. So in terms of our example for Real Madrid, we only see the data for the public games, not the data for the trial matches, right? So it could be that in public games, there's a player who performs very, very well. Maybe they get energized by the crowd, but if it's for trial matches, maybe they don't perform quite as well. Or maybe it's vice versa, right? Like a player is really great at trial matches and not very good at public games. So we are biased towards only being able to use the data that we see in the model. And then another example would be deep learning. And I want to spend a little time on this guy. So deep learning, you've probably heard of frameworks like TensorFlow, Caffe2, CNTK, Theano, Torch. And those are all deep learning frameworks that have gotten a lot of attention recently. So TensorFlow was put out by Google. It's probably the most popular, and it's very well documented, so I definitely recommend taking a look at that. CNTK, also open source, also pretty well documented. It's put out by Microsoft. And then the other ones, Caffe2 and Torch and Theano, they're also fairly good. But if you're going to get started, I would probably recommend getting started with TensorFlow. And what deep learning does is it is a collection of stacked neural networks that do something called backpropagation in order to build up the accuracies over and over and over again. And what does that mean? So backpropagation is basically bullshit detection. So it's a neural network. What it looks like is you have nodes. So like think of little circular dots kind of spread out into a web, and each one of these collections of nodes are placed into layers. And as you go through this classification process, you notice that some nodes tell you correct information and some nodes don't. So some nodes are telling the truth and some are lying. And as you keep going through this classification process, you find out which nodes those are. So you just preferentially pay less and less attention to the nodes that aren't telling the truth. So that's why deep learning is so very, very effective, is that as it moves through each of these nodes, it finds out which ones are telling the truth and which ones are lying, and it just preferentially goes through the ones that are telling the truth. And that's why the training process also takes a great deal of time, and you usually need specialized hardware in order to do it. So the machine learning thing that I showed you before, that's 1,000 records. It can fit into your computer's memory. You don't need a heavy. You could do that on a Raspberry Pi, right? Like that's not something that takes a lot of effort to do, and your model is going to be very, very small whenever it's done. Deep learning, dependent on the amount of data that you have, you could end up using. Like Google has kind of obnoxiously large data science machines that you could use. Microsoft is the same way. We have these things called deep learning virtual machines that have very, very high-end graphics cards, and they're what we use for the training process. So deep learning, lots and lots of data, high dimensional space. So instead of just 17 features, you've got a ton of features. But what it gives you is kind of that feature engineering process for free. So you don't have to know what features you're looking for. You just throw in your data and it gives you the right answer. And you don't know why. You don't know why it gave you the right answer. You just know that it's the right answer every time, and then you just smile and you like go back to your boss and you're like, oh hey, I'm right. Like, aren't I awesome? And you're just right all the time, except when you're not, right? And so this is an example of how a deep learning model overfits, and it's from a paper that was produced by Google pretty recently, right? So this looks like a panda, right? Does everybody agree this looks like a panda? Okay, cool. So this algorithm, TensorFlow, says with 57.7% confidence that this picture is a panda. So it's just over half on board that this is adorable, and it lives in China and eats bamboo and that sort of thing. So if you introduce 0.7% noise to this picture, right? So just this little nematode right here, right? And this is what the picture looks like after this noise has been introduced, right? So it still looks like a panda, right? Everybody agrees, still looks like a panda. TensorFlow now thinks with 99.3% confidence, so almost 100% correct, that it's a gibbon, which is a monkey that looks nothing like a panda. So there have even been studies shown that if you introduce one red pixel, so like say you put a red pixel right there on the panda photo, suddenly TensorFlow cannot accurately classify it as it should. So that is like one of the scariest things about deep learning for me, is that it's so very easy to overfit, and it's so very easy to sort of fool these algorithms, right? Because you can start thinking like, what if you weren't classifying a panda? What if you were classifying missile locations, right? And in satellite imagery, you had a satellite image and a bunch of places that you thought were missile locations. And some bad actor, introduced a little tiny bit of noise into those satellite images. They still look the same to you, but suddenly you're not able to classify them appropriately. That would be bad. And that's why a lot of companies are very hesitant to use deep learning in production, because it's so easy to fool it, and very hard to find out when you did. So I'm kind of sad that you guys, this might be your first machine learning talk, because the moral of the story is that you will overfit. Go for it, dude.
Sorry, in the last example?
Yeah.
So why didn't you just add the noise to the picture and add the frame set?
So you could do that, but that would be kind of, you would have to know that the noise has been introduced.
I mean,
right.
It's quite easy because that noise.
Yeah, but what if you didn't, right? So this was mostly used in the context of, it was used in the context of, somebody, a bad actor, kind of introducing that noise and you not knowing. No worries. But you are correct. If you keep retraining on new data, and that's why it's so important to set up a cadence for retraining models.
The idea would be to add more noise in order to make it more robust.
So you could try, but it would also need to be classified appropriately too, right? So this is Google does something called semi-supervised learning, which is crazy, and should, well, not crazy, it's awesome, but should not be mentioned in a 101 level talk. But what it is instead of having pictures that are appropriately classified, 100% of them classified. It's making assumptions based on pictures that it hasn't seen and using probabilities to classify them. So that's how Google image search is so good, and Bing image search as well, right? Like they're all using kind of the same approach to classify these massive amounts of data.
And the fact that it's doing the wrong prediction,
Yeah.
probably because it's also the feature set is wrong. It's seeing something that we're not seeing.
So yes, but so the question was that the deep learning model would be classifying it as a gibbon because it's seeing something that we're not seeing. But the reality is that it's overfit itself on what it believes to be a panda, what it believes to be indicative of a panda. And even though this looks like a panda to us, right, to a deep learning model, it does not. And that's because it's been overfit.
It basically knows the exact color of every pixel in the image.
Yeah. So that's what it's looking for. And that's not real seeing, right? That's not real knowing. That's not understanding what a panda is. It's just looking for a very specific formula in a picture. So the reality, you will overfit. I'm sorry. But machine learning gives you a ton of tools to be able to spot that overfitting and to be able to work against it, right? And a lot of it is stuff that a human would have to know, as opposed to something that we could just get a computer to do. And that's great. That's job security. So if you want to be a machine learning engineer, definitely recommend it because it needs the creativity of every single person in this audience. The Kaggle, has everybody heard of Kaggle? Okay, so what Kaggle is it's kind of like a machine learning contest board where people have very specific questions and very specific data sets, and you can go online and you can compete to try to get the most accurate machine learning model. And if you're me, you get really excited about it and you talk on Facebook about it and nobody really cares. But Kaggle's great, and Google just recently purchased the company and all of their history of machine learning. And what they found is that 99% of the models, even the ones that win, are overfit. So and the majority of the time, the best way to get an accurate model or a model that can give you high confidence in a prediction is not by using the coolest algorithm or the latest and greatest algorithm. It's by having the best feature engineering that you could have. And that's all a human. That's not a computer at all. So the 5 stages of acceptance for your overfitting. There's denial, right? There's anger, there's bargaining, there's depression. I think we're all in the depression. And then acceptance, right? So understanding that you will overfit, to be able to have discussions with your machine learning team about how to approach that overfit process. And that is that. And just to give you a little bit of context, this is something called the team data science process. So it's every component of the data science workflow. And the stuff that we just covered here is listed under modeling, right? So feature engineering, model training, and model evaluation. That's all where you'd have to worry about overfitting. There's a ton of really interesting stuff that happens in the data engineering side and also in some of the visualization. So I definitely recommend you check that out. There's a resources slide. This is available on my Twitter and also on my GitHub. It has links to the football database that I was telling you about, and a few other open source APIs for football data, and then also a bunch of learning recommendations. So Microsoft now has the ability to get certified as an AI developer, which is kind of nifty. You also have sort of Coursera-style analytics and machine learning courses that you don't have to pay for, which is kind of awesome. But if you are down with paying for it, then I recommend Andrew Ng's machine learning course on Coursera from Stanford and his deep learning course as well. For model selection, we've got a really nice process for that. And I believe I am at time. So thank you so much.